Welcome back to our course on stochastic processes. We now know about filtrations and stopping times, and today we'll start a very important topic, which is martingales. Martingales are a specific kind of stochastic process, which are also called fair games, because on average you neither lose nor win anything in these martingales. Let's see what that means. We will be dealing with martingales in discrete time, which only means that the index set, which is called I in our manuscript, is a discrete set. So just think of t equals 0, 1, 2, and so on. Let's recall a little bit what we already know. Usually we have a probability space, omega fp, where f is the sigma algebra. And ft is a set of sigma algebras, which is a filtration. So fs is a subset of ft for all s smaller or equal to t. And we said that means fs is the sigma algebra which covers all information up to time s. And since we will have more information up to time t, then that's the reason for this inclusion. X is our stochastic process, and usually or very often or always xt, so the stochastic process X, is adapted to the filtration, which means xt only uses information which is available up to time t, so xt is measurable with respect to ft for all t. Sigma of xs, s smaller or equal to t, is the sigma algebra generated by xs. And of course, xt is adapted to the generated filtration. And let me start this lecture on martingales by the following observation. So let us recall what was called the conditional expectation in probability theory. So there we wrote something like the expectation of an integrable random variable. So integrable means x is in L1, so that was the same, with respect to some sigma algebra, maybe that's ft here. So what was this? So this here is another random variable which is measurable with respect to ft, with a property that the expectation over this random variable, which is ft measurable, over some set a in ft is the same as the expectation of x over the same set for all a in ft. If that one holds, we call this random variable the conditional expectation and write it like this. And we've shown several properties. First of all, for integrable x, so this thing here is almost surely unique. That means there's almost surely unique such sigma algebra as some random variable which is ft measurable with this property that this here holds for all a in ft. And one important theorem about this that was called the Tower property, I think, that's the following. If I take this conditional expectation and I'm doing another conditional expectation, and I'm conditioning on fs. And you know fs is subset or equal to ft by this here. So if s is less or equal than t, then the Tower property says that this random variable, which is fs measurable, that must be the same as the expectation of x given the smaller sigma algebra, which is fs. So if we define if we define this one here as xt, then this one here is xs, and we have the following, which is written here. Xt we define like this here. Then we have exactly what was written here. The conditional expectation of xt given fs is xs. That's automatic by the tower property. And that's the defining property of a martingale. So x is called a martingale because it has the property that the conditional expectation of some later time given the information at some earlier time fs is the same as the stochastic process at the earlier time. And of course, all these things only are valid almost surely, and I'm not going to write that down. So X is called a martingale. Let's come to the definition of martingales, and there are actually two things I'm going to introduce. Super, sub, and martingales. And martingales we just had, so this property, the conditional expectation of xt given fs equals xs for all s smaller than t, and I can also say smaller or equal to t, because for s equals t, we had that the conditional expectation of xt given ft, when xt is ft measurable, is the random variable itself anyway. And for adapted processes, this here is automatic, and we always assume that x is adapted. Where we have equality, we can also have inequalities, and if we have a greater or equal, then we will have a submartingale, and if we have less than or equal, we have a supermartingale. Like this. So let's make a picture. Well, maybe not like this. Like this. Here is S and here is T. So assume we have process X at time S is something. And given we have the information up to here, we know what fs here is, so we know the path until here. And now there are several ways this can continue, of course. So it can increase, it can decrease, and do something. And if on average, so we make the expectation of what happens at xt here, we are just moving at a straight line. So on average, let's do like this here. When on average, that's a straight line. So the green one is the average curve. We have a martingale. If it increases, so if it increases on average, we are in this case here. So xt conditional on fs, we assume, so we hypothesize that it's going to increase on average. We have a submartingale, and if it decreases on average, like this here, we have a supermartingale. So these are the three cases. Processes which are, which don't move anywhere are martingales. If they go up, they are submartingales, and if they go down, they are supermartingales. If t is discrete, so I equals 0, 1, 2, and so on, there is some equivalent condition. We do not need all s here and all t. It suffices to have this one here. So xt given ft minus 1 equals xt minus 1. And why is that? Let me write it here because I have here a little bit of space. So if the conditional expectation of xt given ft minus 1 equals xt minus 1, and if we have s is smaller than t, then we can write the conditional expectation of xt given fs, well, that's the conditional expectation of xt given ft minus 1 and all of this given fs. Why is that? So that's the tower property again. So when I use the tower property here, I see that this here is the same as conditioning on the smaller sigma algebra, which is fs. So that's the same as here. But this here is the conditional expectation of xt minus 1 given fs, because by assumption we have this thing here, so we have an xt minus 1 here, and continuing like this, going down from xt to xt minus 1 up to fs, we end up with the conditional expectation of xs plus 1 given fs. And well, again, using this thing here, this here is xs. So for discrete index set, we only need to go down one step. So that's for martingales, but of course also for submartingales, that's the same. So in the first equality, I always have an equal sign. If I have a submartingale, I have this thing here, and so on. I have this thing here, so I have a sequence of greater or equal signs, and then I have this here, of course, for a submartingale. So that's it. So I can also prove the same thing for submartingales, meaning also for sub and equivalently for supermartingales. I have that I only need it for one time step here. Another important thing which we will need is xt t in I is a submartingale. That's the case if and only if minus xt t in I is a super martingale. So that's also clear. A submartingale is something which on average increases. So when I take minus x, it on average decreases, which means by putting a minus sign in front of it, I go from a submartingale to a super martingale. That's what we also need. And we are now going to make some examples. The first one is what we already talked about. That's a random walk. So I take a sequence of random roads which are independent and integrable. They have expectation 0, and ft is the sigma algebra generated by x1 to ft, which is the same as the sigma algebra generated by s1 to st, where st is the sum over the xi's. Then st is a martingale. Why is that? So let's check this. The expectation of st given ft minus 1. That's what we need. And now we need some properties of the conditional expectation. You're invited to recall these from video number, 17, 18 or something from the last semester. That's the same as, well, st is apparently st minus 1 plus xt. st minus 1 given ft minus 1 plus the conditional expectation of xt given ft minus 1. Here I've used the conditional expectation is linear, so I can pull the plus out of this here. Then st minus 1 is ft minus 1 measurable, because if you know x1 to xt minus 1, you know st minus 1. So that's st minus 1. And since xt is independent of ft minus 1, we had the property that the conditional expectation of something which is independent of the sigma algebra here equals the expectation of xt here, which is 0 by assumption. So plus the conditional expectation of xt, that's 0, and we end up having this here xt minus 1. And that means this here satisfies the property of a martingale. It is actually pretty clear, because also from the figure, you already summed up to t minus 1. So that was the sum here. And how it continues, well, on average, we just get the xt in addition. So on average, xt is 0. So on average, you will find that you're not moving, because xt is in expectation 0. So it's a martingale. So that's just from the figure here. Next example. I mean, what we can do with sums, we can of course also do with products. Here we have again independent integrable factors. They have expectation 1, as well as, well, their product. Yeah, on average, the factor we get in addition is a 1. Here it's important that they are independent also. That was, well, it was also the case here, okay. Like this here. That's a martingale, and again, we can prove this by using properties of the conditional expectation. So we need the conditional expectation of st given ft minus 1. So this here is now st minus 1 times xt. That's yeah, st minus 1 times xt given ft minus 1. Then st minus 1 is ft minus 1 measurable. And there was also this very important theorem which said that we can pull out the st minus 1 from the conditional expectation. St minus 1 times the conditional expectation of xt given ft minus 1. Again, xt is independent from ft minus 1. And we have that's the same as the expectation of xt, which is 1. So we have this here is st minus 1, and we have shown that this process here, all the factors here, that's a martingale. Okay. Next example. So we will have many examples today. So that one here is a bit more involved, and it's a bit tricky, but we will need that later in our martingale convergence results. The point is that here we have that the time index is going to the negative integers. xi are IID integrable, and st is the average over the first t xi's. So you're doing more and more averages. But t here is a negative number. So I'm making the absolute value of t, which is then a positive number, of course. And then I claim that this here is again a martingale. And I've printed it out here because there are many indices to recall. And the most important thing here is, since the index set is going to the negative integers, we still have a filtration, which means fs is, so f or ft here is the sigma algebra generated by all t's up to st, and t is a negative number. So that means, well, what does it mean? I do know st, so that's the average over the first t number. I know the average over the first t plus 1, t plus 2, t plus 3, and so on numbers. That's what that means for all t. And from this, of course, I can recall, or I can recover the average over the first t and the t plus first, t plus second, t plus third, and so on the x's. So this sigma algebra I claim is the same as sigma algebra generated by st, xt plus 1, xt plus 2, and so on. Yeah. Exactly. And if time is moving from t to t plus 1, for example, so t plus 1, t plus 1 is then an average over a smaller number of the x's, and I have gained some information about this. So let's see what the conditional expectation of st given ft minus 1 is. First of all, of course, I can just write out st. So that's not hard. By the usual property of the conditional expectation, I can exchange expectation and sum. Okay, that was also not so hard. Here, I have the conditional expectation of xi given the sum over the first absolute of t plus 1 of the x's. So what I have here, that should not depend on this I here, because the xi's are identically distributed. I have an average of all of these, which means I get the conditional expectation of x1 given the average. And we had an exercise about this actually. So for this equality here, we had an exercise in the probability theory course, you can also recall, that the result is that, maybe let me write that down here. So for this equality here, we have the following thing, that this here is the same as, first of all, absolute value of t plus 1 is the same as the absolute value of t minus 1. Because t is negative. So here is, t is negative, and this here is just the same as this here. So that's easy. So that's the reason for this. And just by symmetry, as we argued from in this step here, that must be the same as the average over sum I from 1 to t minus 1, conditional expectation of xi given the sum over these xi, I from 1 to t minus 1, like this. And then I can go back and pull the sum back into the expectation. Then I have the sum in the expectation here, and I have the conditional expectation of a random variable given the same random variable, which is the random variable itself, which is exactly what is written here. And that's an explanation for this equality here. And this here by construction is st minus 1. And for this reason, I have shown the Martingale property of the stochastic process, where st is the average over the first absolute value of t of the xi's. Yes, like this. In particular, I say here, x1, so that's s1. x1 equals s minus 1. And s minus 1, the conditional expectation of s minus 1 given ft, t is a negative number, by the Martingale property must be st. Yeah. So what does that mean? When I know the average of the first absolute value of t random variables, and I want to compute what's the expectation of the first one of them, well, that's essentially the same as the average. Yeah. And we will need that later in some Martingale conversions result, as I mentioned. So, next result about branching processes, so-called branching processes. Here the picture is as follows. We have, let's start with k equals 3 individuals in generation 0. I have generation 1, 2, 3, and so on. So these are 3 individuals, and all of them, they have offspring. They get offspring independent of each other. For example, the third one gets 2 offspring. The other one gets 1 offspring, and individual number 0 here, it does not get offspring at all, such that in generation 1, I again have 3 individuals. Then, for example, individual 1 gets 3 offspring, 3 gets 2 offspring, and 2 gets 1 offspring. And we have in generation 2, we have 6 individuals, and so on. So that's also a stochastic process, which is also a Markov chain, by the way, but it's a very special one, because so zt plus 1 is the total population at time t plus 1. How does that occur? For zt plus 1, I have to count the offspring of all individuals, which are zt, and I'm summing the offspring. So xi sub t is the offspring of individual I in generation t. The xi sub t here, they're IID with values in 0, 1, 2 and so on, because, well, you cannot have negative offspring. And they are independent and identically distributed. And mu is their average. So on average, every individual gets 1 offspring. So mu is their expectation. And the result is that this z here is a martingale if and only if, mu equals 1, which means on average, every individual gets one offspring. Why is that? Yeah, I'm using this calculation here. I want to compute the expectation of zt plus 1 minus zt, conditional on ft. And z is a martingale if and only if I have a 0 here, because, well, zt I can also, so I can first of all use the linearity of the conditional expectation and say that's the same as the conditional expectation of zt plus 1 given ft minus the conditional expectation of zt given ft, but the latter is zt because zt is ft measurable. And I'm writing this like this because I can do some nice tricks here. So zt I have here and I have the sum here. The expectation of I from 1 to zt x1 sub t. And instead of this here, I can also write a 1 here when I do the bracketing differently, because the sum of a 1 over I from 1 to zt, that's zt, of course. Yes. The xi sub t's here, they are not ft measurable, they are independent of ft. Because by time t you know all offspring up to generation t minus 1. And in ft plus 1 you then also know the values of the xi sub n. So they are independent of ft. And for this reason you also had this, that, well, zt equals, that's ft measurable, of course. So we can pull out this sum from the expectation. And then we have that this here is independent. So in the remaining expectation, we can forget about the ft. And the expectation is mu minus 1, because I have a mu 1 and a mu here and a 1 here. And I end up having this here equals mu minus 1 times zt. And that's, of course, 0 if and only if mu equals 1. In general, okay, if zt equals 0, that's boring anyway, because then I have no one who can have offspring. And more holds if mu is bigger or equal than 1, I have a submartingale. And if mu is less or equal than 1, I have a supermartingale. In addition, so I have more martingales to recover here, and there will be nice examples in some later videos. Zt divided by mu to the power of t. Well, that's a martingale in all cases. And why is that? So first of all, I have this calculation here. The conditional expectation of zt plus 1 minus mu times zt. So I have a mu in addition here. And of course, what I have here in the calculation, I don't have a minus 1 here, but a minus mu. I can do the very same trick. Zt I can pull out. And I have here the conditional expectation of xi sub t minus mu, and that's 0. So that's the reason why this here is always 0. Because that is 0, I claim that always zt divided by mu to the power of t is a martingale. Why is that? So the conditional expectation of zt plus 1 divided by mu to the power of t plus 1 minus zt divided by mu to the power of t given ft. Okay, I can write mu to the t plus 1 in front of this. And I end up having zt plus 1 minus mu times zt given ft. And the latter part here, so this one here equals 0. So this one equals 0, and that means that this process here, set t divided by mu to the power of t, is a Martingales in all cases. Yes, so let's leave it like this here. And I have another example. Martingales derived from Markov chains. So remember, for a Markov chain, we need a stochastic matrix. Here I have E is at most countable. It can also be finite, for example. P is a stochastic matrix. What does that mean? That means Pij is not less than 0 for all I and j, and the sum over Pij over all j equals 1. So for such a matrix here, all are bigger than 0, and the row sums, they are 1. They define a Markov chain by this one here. So if you're at time t minus 1 in x, you have a probability of pxy to go to y. Of course, if you sum over all possibilities where you go to, so when you sum over all the y's here, you must have 1. Because the probability that you go somewhere is 1. And that's the reason why the row sums of the matrix P, they have to be 1. Okay. And f is some bounded function, let's say. And let me compute this thing here. The expectation of f of xs plus 1 minus f of xs given fs. I can easily compute this by using the stochastic matrix. So I'm having all information up to time s, which means f of xs. So I know xs. So that's what it means. I know xs. And f of xs, so that's this thing here, I know this. So I can pull it out of the conditional expectation. Here's a typo. That must be a y. I need to compute the probability, the expectation from this here. So where is xs plus 1? Xs plus 1 equals y with probability pxs comma y. Because by this probability I go from xs to y. Then I'm in y, and the f of xs plus 1 equals f of y. So this I can compute. This I can compute. And I can define the stochastic process M, which is mt, t equals 0, 1, 2, and so on, which is f of xt minus the conditional expectation where the xs plus 1 is, given xs. So it's the conditional expectation of f of xs plus 1 minus f of xs. Okay, so I'm having f of xt minus the sum of all these, what they would do on average. Always when I know xs, what will happen on average in the next step. And I claim that this m here, that's a martingale, and the reason for this can be computed as follows. I'm computing the expectation of the increment over ft minus 1. So what is this? So mt minus nt minus 1. Of course I have f of xt minus f of xt minus 1. That's this thing here. And for the latter part here, when I'm computing this at t and t minus 1 and subtract this, what remains is the thing in the sum here at s equals t minus 1, which is the conditional expectation of f of xt minus f of xt minus 1 given xt. That's this thing here. And recall that x here is a Markov chain, which means that the conditional expectation, which happens in the future, given the past, so this here is the past of t minus 1, only depends on where I'm currently at t minus 1, which means that this conditional expectation here is the same as the conditional expectation when I exchange the ft minus 1 by xt minus 1. And that's exactly what I subtract here. So this thing here is 0, and for this reason, m is a martingale. Okay, great. We are almost done. We have a last slide here. And the last slide here shows us how we can derive submartingales from either a martingale or a submartingale by using a function phi, which is convex. And remember, for convex phi, that always reminds us of Jensen's inequality. So Jensen's inequality we had, so if everything is integrable and phi is convex, we had that the expectation of phi of x, and there's some inequality signed here, and that we phi of expectation of x, like so, and this one, that's Jensen's inequality. And the same thing also holds when we exchange the expectation by some conditional expectation. And we are using this to show, for example, in the first thing here, and when we have phi of xs, and we want to show that this here is a submartingale, we have to show that that's less or equal than phi of xt given fs, because then on average it increases. Well, it's almost written here except for the conditional expectation. So by Jensen's inequality, this here is greater or equal than phi of conditional expectation of xt given fs, like this thing here. And for 1, x is a martingale, which means that this conditional expectation here is xs almost surely anyway. So that's for the first one. And for the second one, it's almost the same. I mean, I use the martingale property only for this thing here, so I can first of all again write everything except for this inequality sign. This one here holds phi of xt given fs. But we have to think about how we can compare these two things here. And first of all, because it's a submartingale, we know that xs is less than or equal than the conditional expectation of xt given fs. That's what we know, because we have a submartingale. But we also know that phi is non-decreasing, so it's rather increasing. But if it's not decreasing, that means if I have two values, first one less than or equal than the other, then it does not change if we write phi in front of both sides, because phi is non-decreasing. And that's exactly how we can compare these two things here. So we also have less than or equal here, and we have the submartingale property also in the case number 2. Okay, great. Then we are done with today's video, and now know a little bit about which examples we can find for martingales. And we will come in the next video to some important properties The most important properties are that martingales have convergence results, so they converge as t goes to infinity under rather mild conditions. That's what makes them so powerful. So see you in the next video. Bye.